Hello, everybody. This is Professor Ma, and this is the sections on the second derivatives, the relationship between the second derivatives and the graph of a functions. And let's review the first derivative and what the information first derivative gives us, so that we can clearly distinguish between the information later on what the second derivative information gives us. Okay. And so here, the way we imagine, so this is that there are a lot of visual tricks we use to look at a curve and to label what the derivatives is positive or negatives, and same thing with second derivative. So in the tricks in these cases, we view this as a track of roller coasters, and so here's a roller coasters, and it's the roller coaster is going in that directions. Okay, and where the tracks are flat, that's where the derivative is zero. And where we are going uphill, if the roller coaster is going uphill, and it's the same as increasing. So increasing and uphill. So these are the descriptions of derivative. First derivative is positive. Okay. And then downhill is first derivative is negative. So we can basically summarize the derivatives in these first derivative in these pictures. Okay, y prime is zero, it's going uphill. Y prime negative, derivative is negative. That's where the track is going downhill. And what it's equal to zero is where the points are flat. But but in this particular over here, you actually give the descriptions. Okay, it's a maximum if it's a coming uphill followed by going downhill. So hence, this is a maximum right here. You go up, then come down. And then for minimum, it's the other way around. Okay, you go down and come up. And then you have this shoulder point where you go up, but then you go up again. You just flattens out at those two shoulder points, but you continue on with going uphill or going downhill. So these are what first derivative tells us about the graph. Now let's take a look at a second derivative. Okay, the place we start, let's take a look at the maximum point. In order to get to the maximum and the roller coasters, think of it. Okay, if we will get pulled off this track, and everybody has probably has this same experience before, is when you get close to the top of roller coaster, you will have this feeling of going up, then you have feeling of this forward motions start flattening out, and until you get to the top, then you are top of the roller coaster, then you're ready to go down, slide down, then you start going downhill. Okay. And what's happening to the derivative? That's what's happening to the series of slope, is that the slope is positive, large positive, gets smaller and smaller and smaller until it's flat, and then it start going negative. In other words, the derivative across that point is decreasing from positive to negative. So here is a characterization of what a maximum point is. And we have, in particular, if the first derivative is zero, it's flat. And plus the second derivative is negative. Okay. Again, y, this is provided y prime is equal to zero on top of the end, and second derivative is negative, then this point is maximal. And we have a similar description for minimal. Okay, it would be inequality pointing the other way around. So what does it mean for the second derivative to be positive? Well, in particular, at a point where the second derivative is positive means here we're going from very negative slopes and start slowly turns into climbing. It goes from falling, going to climbing. So in other words, the second derivative at these points are positive because the first derivative is increasing. Okay, so that means the secondary derivative is positive at that point. In this case, we call this point where the second derivative is positive, we call this concave up. Okay. Now, for how can we tell a piece of curve where it is concave up or concave down by looking at it? Now we're going to use a different analogy than the roller coasters. Now we're going to view this as suppose this is a trail, okay? And you can think of this as a drone or whatever, or you're just looking from the top down and there's a little bug and it's going along this curve, and that's where the trail is, okay? And the second derivative is positive if the bug is making left turn, okay, as it crawls from left to right. So second derivative corresponds to where the ant, as it crawl along the curve, is making left turn. Then you have the other definition of concave down, where the second derivative is negative, okay? And that's when the ant crawls along this, okay, this is not roller coaster anymore. Okay, we're talking about a bug. You're looking from top, and as the bug crawl along this stretch, its second derivative is going to be negative. Okay, why? Because the derivative is getting less and less. And in particular, the bug is making right turn. Okay, so, and the point where they join is interesting because that's where the bug transitions, okay, in this case, from the second derivative positive, okay, and making left turn, the bug's making left turn, so the second derivative is positive. At this point, the bug has to start making right turn. So what is this transition point, changing from left turn to right turn? That's where the second derivative is 0, because at that point, the second derivative is not positive nor negative, okay? So such a point is called inflection point. In particular, an inflection point is where the second derivative is 0, and the second derivative furthermore changes sign. That is, think of the bug again. The bug turns from making left turn into making right turn, and that point is the inflection point where they join up. Okay, and I also want to point out that the join of these two concave up and concave down, it doesn't have to shape like that. I can just take this stretch, for instance, which is concave up, and the joint with, for instance, this stretch, and which is pointing concave down, and that is an inflection point. Okay. Again, think of oneself as the bug crawling along this curve, and the concave up is making left turn, and when it gets to that point, it starts making right turn. It's concave down. So this stretch is concave up, that stretch is concave down. So the point is a joint point like S shapes, the points where the bend turns the other way. Okay, and similarly, for these, we could have going up, concave down, joined with a piece of that. Let's say from here to here, okay. Of concave up. At that point, it's an inflection point. Okay, it could be like that, or it could be a piece from here again, or from here and piece from here. as on the concavity, the turn changes. That's an inflection point. Okay, so here are brief explanations. You can see the concavities of the powers, the even power versus the odd powers of power functions. Okay, and let's do one exercise. For instance, okay, back to the first derivative. This is increasing, so the sign charge here is plus, and derivative 0, that is increasing again, so the sign charge plus. This is for the derivative, okay? I want to point out the difference between the two. Now we get to where derivative 0, then begin to go downhill, so derivative is minus, and it's flat, so derivative 0, and then it go downhill again, so it's minus again, and then it start to climb again, and oh, by the way, derivative 0 here, then the derivative is plus. That's what the first derivatives tell us. Now, how do we visualize the second derivative? Remember, this is going uphill, downhill. We view this as a roller coaster, okay? Now we're gonna view this differently. We're gonna view this as a, for, you know, as I said, as a bug crawling along. This, okay, that's kind of, well, let's make a big bug. Okay, and it's crawling along. And then the questions over here is the bug making left turn or right turn? Okay. If it's making right turn, that's concave down. It's making left turn, it's concave up. So let's start. So for this bug, it's not, and from this stretch up to here, it's making right turn. So it's concave down. Okay. And it gets to this point where it flattens out. And now it's going to start making left turn. And along here, somewhere over here, oh, by the way, it's making left turn over here. So at this place, this is concave up. But notice, at somewhere along between the two flat points, it must stop making right turn now, okay, to somewhere over here. So this, again, is a stretch that's concave down. And then from this stretch, the bug crawls, and now it's making left turn until it gets to these points. So this is concave up. And now it's making right turn to somewhere over here. So this is concave down. And now the bug is making left turn. And keep turning left, keep turning left, keep turning left. Let's assume that. Then this is where it's concave up. Where is it? Derivative, second derivative 0 at the joint. This is where the second derivative are 0. So this is the sign chart for the second derivative. I know it looks kind of a lot of different, okay, so this is going to be minus, minus, minus over here, but it's going to be plus, plus, plus. I know this one is a long stretch of a long curve. It does quite a few winding and twistings. Okay, but this is what second derivative information gives you. And then the example goes through go through the these particular functions. And if it go through the sign chart, first of all, we just look at the sign chart of these formulas. And so in particular, sign chart tell us the graph is going to be positive over here, negative over here, and it's going to be positive or negative. So the basic shape, that's what the sign chart of y. No derivative. Now, then we're going to calculate first derivatives. Okay, it tells us more informations. Okay, so that's where the flat points are from the derivatives. Okay, so that's the graph. And then the second derivatives tells us where the left turns and right turns, think of as a insect, a little bug crawling along, and whether the bug is turning left or turning right. And that's a second derivative. And then this is where the second derivatives tells us in this particular interval. In terms of graph, okay, where are they? They located over here. Let me see if I fill it in, and here they are. Okay, that's where the concavity changes. That's what inflection points are. Okay, so this is a calculation, example of calculation. And here's another example. And so get a sign chart of the function first. Then we look at the first derivatives and find where the flat points are. The flat points where is this tops equal to 0, so at plus minus 2. And if I plug these numbers in, I will get 2 points. 1 point up here, 1 point up there, where slope is 0. Okay, so it's positive. So the things has to go from there and go up there and come down here. Okay, it's flat. So that's the middle portions at 2, minus 2, and 2. So this is basically what sign chart tell us. Okay, and also this goes to 0 as x goes to infinity. So this must come down like that, and this must. So this is basically what the graph will look like. Okay. Got 2 flat points, and as x goes to infinity, y goes to 0. Okay, so it must flattens out. Then somehow it has to go to 0. It couldn't go to 0 with that hump. It must slow down the rate it drops and stop pull away from try to land the graph along the x-axis. Okay, so you must do a little curve like that, and that's where the inflection point comes in. And so this is a calculation show where these inflection points are. Okay, and here's another example. Notice it has a strange exponents, and this involves where the second the derivative doesn't exist. The first derivative doesn't exist. Okay, so I can do the sign chart. Okay, and so derivative doesn't exist at 0. Okay, so we get one root for the derivative. Okay, if you take this derivative as 0, we'll get a root over here. Okay. And so that's one place. If I plug in 1, I get 3. That's where the graph is flat. And the sign chart is plus here. Okay, so the graph is going to go like that. So it seems plus from there to there. Okay, 2, 5 halves. Okay. Now you go minus, so it keeps going. Okay. So this is the graph of using the first and second, using the sign chart and the first derivative. And here's what the second derivative tells us. Okay, the second derivative, since if you think about it, that if you a bug keep crawling along this curve, you'll keep making right turn. Okay, that means the second derivative is negative all the times. Okay, so Therefore, the second derivative tell you on this side, the curve must be comes keep making right turn, and afterwards you have to go up and keep making right turn, okay? Because the second derivative is always negative, so it's always coming down, and you create a cusp over there, and so if you remember that's what limit x approaching infinity and 0 plus limit x approach 0 minus, and you get the derivative at prime, and one of them is plus infinity, one of them is negative infinity. Okay, and that makes point a cusp. Just want to point that out. So this is what second derivative tells us. Okay, that's it. Bye bye. Later.